today the topic are control structures. And control structures are same as in all other languages, but there is a huge difference between functional languages and procedural languages. The difference is that in the case of functional languages, each expression returns a value, and each control structure returns the value. So if you have a sequence in C or C++ or Java, you put two curly braces, and then you have statement, 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 statement. So this is a sequence. Sequence returns nothing. It is just doing side effects. Therefore, it is not an expression that returns a value. It is doing side effects. What is for loop doing? For loop returns also nothing. It makes plenty of side effects, changing content of memory, but not that it is returning a value as a function. How about if statement? If statement is going left or right in then part or else part, but is again doing nothing that is returned. All languages that support functional programming are returning a value. And you are going to see if statement that returns a value in Ruby. And of course, in the case of Scheme, which is functional programming language, you are going to have everywhere that every control structure returns a value. So if we have sequence, sequence starts with keyword begin. And then expression 1, expression 2, expression 3, what is returned is the value of the last expression. So if I want to try that, I can say begin here, begin, and then put here expression, for example, add 1 and 1, and multiply 2 times 3, for example, like this. So what is going to be the result? We have two expressions. First is 1 plus 1, which returns the result 2. And here is 2 times 3, which returns result 6. And if I expand this with the third expression, for example, 8 times 8, like this, then I am going to get that the result will be always the value created by the last expression. However, you can also use much less frequently begin 0. Begin 0 is giving you the value of the first expression. So this begin 0 returns 2. Therefore, if you have begin and then expression 1, expression 2, expression 3, so any number of expressions, all these expressions are going to be evaluated and the last one will be returned. If you have begin 0, then you are going to return the first value. So that is what Scheme and Ruby give you as a possibility when you return values. So going back to reader, if I have here begin set x is 5, this is not going to work in Ruby. So just to show you what is going to happen, if I have this kind of expression, it is going to create error because this 1 plus is one of those strange increment operators that exist in Texas Instrument Scheme, but not in Ruby. Of course, is in Texas Instrument Scheme, you also have add 1. And this add 1, of course, is applicable both in Texas Instrument Scheme and in Ruby. I just wanted to show this 1 plus at the time when we had Texas Instrument Scheme, but add 1 is okay. So if I have x that is set to be 5, I had variable x previously defined. So set x to be 5. So now x is 5. And this is the expression that returns nothing. But if I have here add 1 to x, this returns 6, because this is operation that is returning a value. And therefore, if I have this, last value is 6. If I try to return here 0, so to return this first component, you get nothing, because when you set this, you are doing side effect. You are not returning a value. So this is an important thing to see, the side effect. When you say x equals 5, this is in many languages like Fortran returning nothing. In the languages that try to be a little bit functional, like C++, expression is returning a value. So assignment is an expression. And this is the only thing that they offer, not much more than that. So let's go back to our reader and let us see what happens with if statement. So if statement has condition, and if the condition is satisfied, then we evaluate expression 1, and that is returned from if statement. If condition is not satisfied, we execute expression 2, return expression 2. So if I have 1 that is defined as 1, 7 that is defined as 7, and then say if 1 is greater than 7, say yes, otherwise say no. Of course, 1 is not greater than 7, and the answer will be no. So this if statement here returns the value. This value is either yes or no. And this is an expression. And this expression returns a value. And this is different from behavior in procedural languages. Procedural languages will display something, but will not return the value. So if 7 is 3 plus 4, say yes, otherwise say no. So 7 that was defined as 7 here is compared with 3 plus 4, which is 7. So 7 equals 7. This is true. So if this is true, we return yes, otherwise we return no. You can use, of course, if statement, but many people don't use if statement because there is a generalized if, which is if else, so-called condition, cond. If test 1 is satisfied, then execute expression 1, expression 2, expression 3, all expressions that are in this sequence, and return the value of the last expression that is evaluated. So if test 1 is not satisfied, then we execute test 2, and then test 2 is satisfied, and it creates sequence expression 2, 1, 2, 2, 2, 3 up to the end, and the last value is returned. If all tests fail, then we execute the else part. So else, expression 1, expression 2, and we return the last one. Of course, what happens if we have only one test? Well, this is completely equivalent to if statement. I can say condition here, test 1 satisfied, perform whatever is here, else the other part. So you can have condition, test, expression, else, expression. That is typical if then else. So because of that, I've seen plenty of people who are not using if statement at all, are always using condition, and then if you have one test, that is if then else statement. So here is an example: x is 3, y is 4, and then if x is greater than y, return greater. If it is less than y, return less, else return equal. So condition has 3 possibilities, as you see here: greater, less, or equal to. So if it is greater, and here, of course, x is less than y, the answer will be less. And this is a nice example, tiny little example that shows how condition works. And you can have any number of this condition and at the end else. Okay. So now you can say y to be 3, and then after we apply this operation, we get equal because it is not 3 and 3 are equal, so it is not greater, it is not less, therefore it is equal. We also have case statement, same as a switch case in C, C++ Java, and we have that this case statement has a selector variable, which is this expression. Expression is evaluated, you get the value, and this is selector value. Now, if selector value is equal to this atom 1, then perform these expressions here and return the value of the last expression. If it is equal to atom 2, perform this sequence of expression, returns the last, and so on and so forth till atom n. If none of these atoms is equal to expression, then perform the else sequence and return the value of the last one. So again, the case statement from here to here returns a value. It is an expression and returns a value. For example, if I have a test function, defined test, which is lambda of x, and x is selector variable. So case x, if x is 1, 3, 5, 7, 9, return odd. If it is 0, 2, 4, 6, 8, return even. In all other cases, else say it is not from 0 to 9. So this is a trivial little program that has many of these case values and returns the value depending what is satisfied. So if I say test 5, 5 is here, and the answer will be odd. If we say test 6, the answer will be even. And then if I say test 12, 12 is not from 0 to 9, and the answer will be not from 0 to 9. Of course, this is very inconvenient to write one option at a time, so you can put them in a list. So the expanded case statement has here atom list, atom list, atom list, and if expression belongs to atom list, then you perform the sequence of expressions here and return the value of the last one. So this case from here to here is again an expression that returns a value. So that is the point in functional programming. Functional programming, everything returns a value because everything is a function. And this case is also the function and returns the last value here. So when you learn to use that, you see that it gives you nice possibility to combine operations and removes restrictions, etc. So I have here a test function that is lambda of x, and then case x has this two lists, 1, 3, 5, 7, 9, or 0, 2, 4, 6, 8, which gives you the result even. So this case returns either odd or even or not from 0 to 9 in all other cases. Please pay attention that this list here, 1, 3, 5, 7, 9, is never executed, and therefore it doesn't have a quote in front of it. Otherwise, it should be quoted list. It looks strange, but it is not a quoted list, and therefore it is not a list that is being executed. It is just list that tests belonging of this x to this component. So if I say test 7, it returns odd. If I say test 4, it returns even. If I say test 123, it says not from 0 to 9. Okay, so these lists here are lists of components that are never executed. Okay, so it doesn't have to be that way. Now comes one tricky thing, which is do loop. The question is, when you have loop in any procedural language, for example, do loop in Fortran or for loop in Java or any kind while or do while loop, all these loops are performing body. body, body, body is executed many times. Why is body executed? It is executed to create side effects. What you do, you are changing the side effects, various memory locations. That's what you do inside that body. Therefore, a loop is not executed in procedural languages in order to return a value. It is simply performing side effects, and when you exit from the loop, you find memory that is modified, but not that you return a value. In the case of scheme, which is functional language, do loop must return a value. And therefore, it works like this. You have do, and then you have variable that has initial value and update. And this is put inside parentheses. So you have variable, initial value, update. And then second variable, initial value, update. So these three dots tell you that this can repeat any number of times. Variable, initial value, update, another variable. So you can have any number of indices in the loop. After that comes the termination test. Next line is termination test. Termination test can be either true or false. If the termination test is true, then here is one tail of expression, 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 and the last of them is returned. So if termination test is satisfied, we perform a sequence of expressions, and the last is return. The body of the loop is in third line. So first is initialization, then termination test, then body that has any number of statements, and the last statement here, if everything in termination test is something. So you cannot return this value. These are side effects. But here is what we do with returning value. So what you have is this. You have initialization of a counter, termination test, and if termination test is satisfied, true, we have this sequence of expression, V1, V2 through Vm, and then this is the return value. Now, inside the loop is body, body 1, body 2, body 3, body n, any number of operations, but they don't return a value. They are here for side effects. And then comes update. So initialization, termination test, body update, body update, body update. So this is the typical execution of loop. And then when termination test is satisfied, there is this sequence of expressions that is executed, and the last one of them is the return value. So that's how this works. Let us see, can we use that in this program. I want to write a program that is displaying 1, 2, 3, 4, 5. So how to display this? I can say I have a do loop, do, and then I have k is 1, and this is initialization of variable k. K is going to be the counter. And then it has initial value 1, and then it has here update plus k1 or plus 1k or add 1 to k, whatever you want to. In any case, it is computing the new value. And this new value is given in each iteration to k. And then here is the termination test. Termination test is that k is greater than 5. If k is greater than 5, then we are going to display an empty string. And that means returning nothing and terminate the program. The body is going to display k and display a little bit of space. So I have display k and display space. So k is 1, and then this one space. Then k is 2, and then space after that. 3, 4, 5, etc. We are moving from left to right here. And this is the do loop that works the same way in scheme and in Racket. Another thing that I want you to note here is, again, this story about double parentheses. Do you see this parenthesis here? This is a parenthesis that is, and this parenthesis here, they have any number of indices inside. So you can have this k, you can have n, you can have m, you can have whatever number of indices which are incremented in specific way. However, if you have that this instantiation here that the index is only one, then you still have to have this pair of outer parentheses, because this is the syntax that tells you this is one construct here, but you can have multiple construct of that nature. Then if k is greater than 5, you return empty and go out. Now, to show you a little bit the way how this works, we have here an example of computing arithmetic series sum. So if you compute 1 plus 2 plus 3 plus n minus 1 plus n, this is obviously sum of n minus 1 component. So n minus 1 components is from here to here, plus n, which is the last value. So you can say sum of n is sum of n minus 1 plus n, and this gives you this normal recursive program. So define arithmetic sum of n, condition if n is 0 or less than 0, return 0. In all other cases, return the sum of n plus sum of n minus 1 components. So arithmetic sum of n minus 1 component. So this is the nice little recursive program, usual tail recursion. And we have that arithmetic sum of 10 is 55, of 100 is 50-50. And this is working the same way in all languages. So even you can, with Control C, move this to Racket like this, put it here, Control V, and this is going to be array of 10. The sum of arithmetic series 55, and if you go to 100, you get this nice 50-50. And if you want to add 1,000 of numbers, you are going to have 500. And if you have here any number of numbers, you are going to get the sum, which is 5, and then plenty of zeros, and 5 and plenty of zeros. This is a strange sum that has always this nice result. So going back to, reader, here we go. We can write that by using multiple initialization and updates. So generalization of that is that you have, if you have this initialization I1, I2 through IK, if you have more than one, then everything looks the same. You have termination test, body, 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 sequential execution, first, second, last. And then you have updates, update 1, update 2, update K. The only thing that is strange and different from procedural approach to this is that these instantiations and these updates are done in unspecified order. That means the standard of the library doesn't tell you in which order is this going to be done. So this is also like this insert in cout stream that we played with in procedural programming. You have that these instantiations and these updates must be independent. So please try to make them independent, because otherwise we are looking for trouble doing something that is not safe. So if I want to compute this arithmetic sum, I can compute it using do loop. So I can say do, I is 1, and in each iteration I'm going to increment I is I plus 1. And then I have sum that I'm computing, and sum is instantiated at the beginning as 0. In each iteration, we set sum is sum plus I. So we are incrementing sum plus 1, plus 2, plus 3, plus 4, etc., computing arithmetic sum. When I is greater than n, we return sum. So do loop that has instantiation, termination test, and body. And it works fine, RE1, RE2. So we can be tempted to make this bodiless loop, to remove this from the body. And here is what I do with that. So I define arithmetic sum of n and say I'm going to have I, which is initialized as 1. In each iteration, I'm going to increment by 1. But I have sum, which is 0. And in each iteration, it is incremented by I. So after that, you have termination test and you return sum. Where is body? There is no body. Body should be between these two last parentheses. There is no body. So is this working? Yes, it is. Why? Because we are lucky. That's why it is working. Because this here, the first expression, and the second are not independent. Practically, what I'm counting on, that there is first going to be incrementing of this I, and then I'm going to use this I to add to this sum. So I'm practically hoping that it is going to do this first and this second. Okay. So I should not count on that. If this is performed before this one here, the result would be wrong. Therefore, don't do things like this. This I and this I are counting on execution, first incrementing and then summing. And if it is not in that order, then we are in trouble. So try to avoid this kind of things because they should be theoretically independent. Here are a few examples that I'm going to skip for the moment. And we'll perform this binary decimal to binary conversion. So we did that earlier. So in procedural programming, recursive program, for example, has 15 and binary value is 1111, or 10, you have that it is 1010, or 7 is 111. So I want to write a program that is making a table of numbers converted to binary value, or like this binary 32,767 is this 1, 1. This is the largest value that can fit a 16-bit location. And if you add 1 to that, you get this 1 with 0, 0, 0, which is practically the smallest negative value. And this is the largest positive value in short format in C, C++, similar languages. Anyhow, there is no any negative value here simply because these are binary digits without any overflow, and integers don't make overflow here. But anyhow, we want to write such program. So how to write that? Well, we are going to find these two functions that are doing the same thing. This binary here is lambda of n. And then if n is 0, I return this empty object. So display empty string is empty object. This is returning nothing because it is displaying bits. So else I'm calling the same function with n divided by 2. So it is chopping one of digits and taking the value that is n divided by 2. And then a divided by 2 by 2 by 2, sooner or later you get to 0. And after that, you start returning from this call. And then n modulo 2 is going to be the first digit and second digit and third. As you keep returning from there, you are going digits 1 by 1, first, second, third, etc. And so this is the binary program. This bin is doing the same thing. If n is less than 0, display the argument must be positive. If n is less than 2, then display n, and else compute this bin of n divided by 2 and display n modulo 2 when you start returning. And the loop is written in the way that we already used in Prolog, you know, this fail and repeat, etc. When you define the loop and do something inside that loop, at the end you can say call again the loop. This subtract 1 from x, so x minus 1. And therefore, I'm going from initial value of x, and then I'm asking if this x is minus 2. If it is minus 2, I return an empty object, and else display x and put a little bit of space, and then call this bin that is displaying all binary values, put new line here, and call loop again. Pay attention that there is new line here, new lines, putting end of line, and it is called new line as a function. And when you execute this program, you get this 16 loop of 16. So 16, 15, 14, 13 coming to 0. And when you come to minus 1, the argument must be positive, and minus 2 is returning from this function. You can apply this binary converter to rather big numbers, and you get binary value that is equivalent to this decimal number. Pay attention that all strings of digits don't have to be interpreted as negative numbers. I had on exam people who believe that this is a negative value. Why negative? Because the first digit is 1. Well, it is negative value if we have this kind of data type, but this is not the data type that interprets this as negative value. So it is just one string of bits. Now, we have one little more complex function. This is finding maximum of x. So I want to write the function that will find maximum. So here is find maximum of cosine function. So this is the function, and this is the range where I'm going to look for maximum, from -1 to +1. Of course, maximum is f of 0. So cosine has maximum in 0 because it's going up and down. So cosine has maximum in 0, and the maximum has the value 1. So I want to write the function that is computing the cosine of this function here. The beautiful thing that is finding maximum of this function here. The beautiful thing is that you can have also that this function is directly a constant, which is a lambda expression. So I say lambda of x is 1 divided by x minus x. So this is negative value that is going and having maximum, and maximum of 1 is -2. So you can put here directly function that you want to do. How to find this maximum in this range from -1 to -1? First of all, when you define function, you can define it with function of 3 arguments, f, x1, and x2. So this f is function, and this here is numerical value. So they look the same. There are no restrictions. What is f, what is x1, what is x2 will be clear when we call this function. So it is to have the data type when we call this. So I have a condition, and then if x1 and x2 are very close, if x2 minus x1 is less than 10 to -10, I'm going to return the result. So we'll say maximum f of, and then the result is x1 plus x2 divided by 2. And I want to do this with 4 significant decimal digits. So I put here one auxiliary program that is computing and displaying the value with n significant decimal digits. So what I do, I take this x that I have to display and put here, multiply that with 10 to n. And then round that, take the integer value, and then divide by 10 to n. So you're going to get this is homemade set precision. Set precision in C++ is telling you how many digits you want to have, and I put here n of them, and that's homemade set precision. So that's not important. I use it here to show this value. So I have this disp that is going to show me that, and then say equal, and then display this result again with up to 2 digits. In all other cases, we are going to find 2 auxiliary values. One is A1 and the other is A2, and this is let scope. And with this A1, I'm going to say that this is left border x1 plus x2 minus x1 divided by 3. So this is this trisection method. And the second, A2, is the right border minus this 1/3 of the interval. So now I have these 2 values, A1 and A2, that are between x1 and x2. Now, I'm asking whether function in A1 is less than function in A2. If it is less, then I move this first value to x1 to A1 and compute f max of this function of A1 through x2. Otherwise, compute maximum between x1 and A2. That means x2 is moved to A2. So this should compute the maximum of the function. And then here are various examples where we compute the maximum of various functions. So for example, if I go here and have the function lambda of x, which is x times 1 minus x. So what is x times 1 minus x? It is parabola that is going through point 0 and point 1 and has maximum right in the middle in point 5. Okay, so this is this lambda expression, parabola that has maximum in 0.5, and this maximum is 0.5 times 0.5, which is 0.25. So I'm asking, find this maximum between 0 and 10. Okay, then it is going to go left, right, left, right, left, right, and it is going to give me maximum in 0.5 is 0.25. Pay attention that I have here 2 significant decimal digits. That's what I wanted to have here. So this is this 2 here. Here, this disp, display, oops, display this with 2 significant decimal digits. Okay, so this is example how this program works. And pay attention, this beautiful possibility to put here an anonymous function directly. And you say, find me maximum of this function, or some other anonymous function, or function that has name, or function that you have made, or function that does not have maximum. You have find me maximum or square root function. Square root function is increasing monotonically, strictly from 0. And I want to find maximum between 0 and 1. And in that interval, the maximum is 1. That's the largest value inside that interval. So the function is finding the maximum in the interval from 0 to 1. And it works this way. So the next topic are lists. Of course, this is the most important topic in this language, simply because lists are everything in list processing. And if you write a list like this without quote, then you are assuming that the first item is operator. So this is operator, and you have operand, 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 any number of operands. So this operator is applied to these operands, It creates the result, and this result is returned. So each list returns a value. And that's what functional programming is all about. Okay. And then we have the possibility to quote that. If we quote prevents execution. So you keep this list as it is. It has a variety of operands or operator operand, whatever you want to have inside. However, you can never execute list of this kind here because this operand is going to be interpreted as a function, and this is not the function, and therefore this is going to create error message. Okay. Uh, if you want to cancel this quote, you use function eval. Evaluate is removing this quote. So if I have quoted list 1, 2, 3, I return 1, 2, 3. This here is empty list or false in Texas Instrument scheme. And this is not a legal object in Ruby. So be advised not to use this one. You have to quote it. So in Racket, sorry, not Ruby, I always mix Ruby and Racket. So if we go to Racket and say, what is this now? This is an empty list, and it returns an empty list. Same as when you say number 3, it returns number 3. But if I put empty list like this without quote, then Texas Instruments scheme will say, yes, this is legitimate empty list or false. And in the case of Racket, you are going to get error message, missing procedure expression. So probably originally empty string, which is an illegal empty application, illegal empty application. So this is illegal empty application, and this here is empty list, which is a legal element without any problem. Now, in the case of these lists, pay attention that you cannot use list that is not quoted if it doesn't have operators inside. So I'm trying to ask whether this what comes here is a symbol. Of course, this list is not a symbol, but if you want to ask that, you have to have quoted list, and the result will be false, of course. However, if you say, is the symbol 1, 2, 3, then scheme is interpreting this 1 as a function, and function that has arguments 2 and 3. And this is, of course, wrong. And therefore, it has to create error message and attempt to call a non-procedural object. So attempt to call a non-procedural object means you try to execute as a procedure something that is not a procedure. Now, if you have a question whether list, a legitimate list, is a symbol, the answer is no. There are plenty of operators that work with lists. For example, length or reverse or null or list. So all of them are listed in the reference card. So you have to read this to see what does exist. So length is telling you how many elements you have in the list. So you can write your own length function, and length function will say you have head, and then this is one component plus number of components in the tail. This is the length of the list. And that's how this works in scheme. So length of ABCD is 4, length of 1, 2, 3 is 3. Length of 3 times 2 is 0, because this is operator, operand, operand. So we have 2 multiplied by 3 is 6. This returns a scalar value. The length of scalar value is 0. This is by definition 0 because there is nothing inside. So length of empty list is 0. This is error in Ruby. You can ask whether something is an empty list. The recognizer for empty list is null. Null with question mark is recognizing whether this is an empty list or not. Then you have here whether empty list is 1, 2, 3. No, it is not. Another operation that is very important and frequently used is making list constructor. So list is operation that is creating list with components that you put here one after the other. So this has 4 components. Number 1, number 2, list 1, 2, and the list AB. So this list creates the list 1, 2, 1, 2, AB, 4 components. Now, expression within the list may be any object. There are no limits. They can be lists, that can be atoms, that can be functions, they can be whatever you want. So that's the story that starts with removing restrictions. So there are no restrictions what you can put in the list. So a list can be list of functions, so put inside lambda expressions, and that's perfectly a legitimate list. So if I have here function maximum, that is finding maximum of 1 or 1 plus 1 or 2 times 3. Obviously, 1 plus 1 is first executed 2. This here is 6, and maximum between 1, 2, and 6 is 6. Okay, so maximum is a function that is applied to arguments that come after that. So you can have variety of operations with lists, and you can have a constructor. Is a question? If you have a question, just unmute your microphone and ask question, no problem. So we have here constructor. Construct is same what we said that existed in Prolog, is constructing a binary tree. So you have 2 branches, you have 1 point and 2 branches of binary tree, and one has the value A, the other has value B. So it is giving you a pair that has A, B. Here is A dot B. And then you can construct A, construct B, construct C, and put here nil. Nil is the legitimate empty list. So this is empty list that you put at the end, and when you construct this, you get A, B, C as a list. And this is how the list is internally stored. Practically all trees, binary trees, must have somewhere these dots that tell you how you branch left and right. So these are construct operators. So instead of working with pointer and lists, you can write directly in this way. It is more convenient to write quote A, B, C than to say construct A, construct B, construct C, and nil. But this is completely equivalent. This here and this here is the same thing. Just this shows the anatomy of the tree inside. If you want to see the head of list, head is always the first component. So head of ABC is A, and CUDR is the tail of the list, which is list BC. Same as in Prolog, tail is always the list. So if you have this vertical line, left of it is head, right of it is tail, and if you want to see car of this, you get A, CUDR is B. So car and CUDR work with lists and work also with trees. Now, relationship between car, CUDR, and construct is that you can construct car of list and CUDR of list, and you will get the list. If you construct head and tail and take car of that, you will get head. If you construct head and tail, and CUDR is going to return you tail. Therefore, this is the way how we can construct objects. And here is construct head and tail, and car of that is this head. And here is CUDR of this construction, and you get tail. And of course, you can have car of this, it is returning the value. So if we have, for example, something like this, so you have the list and you want to see car of list that has variety of elements inside 1, 2, 3, 4, 5, 6, 7. Okay. So what is har? It is head of list. If I want to get CUDR, uh, CUDR, CDR, okay, I get the list, not the element, but the list is going from second element to the last element. So if I want to get second element of the list, how to do that? Well, I can say, give me car of CUDR. Okay, so we'll put here, give me car of CUDR of this list. Okay, so go here and perform this. So car of CUDR is the second element. How to get the third element? Well, car of CUDR, and you can go like this any number of times, but there is a simpler way. You say car of CUDR. So CADR applied to this list. I don't want this to write again, but we'll go here. Okay. This is better. Okay, so what is going to happen now? It is going to return me car of CUDR, which is second element. So this is number 2. Now, if I want to find car of CUDR, I go here and put CADR. Okay, so this is going to return third element. Beautiful. So I can keep now adding these, any number of them that I want, CADDR, and get the fourth element. So you can get first element with car, second with cadr, third with CADDR, fourth with CADDR, and then you can hope to continue from here to eternity by putting 200 of this, but this is not going to work. So you can get first, second, third, and fourth element of the list by using these functions, car, cadr, CADDR, CADDR, and you cannot put 4 of them or 5 because this is undefined function. So you cannot have this. Of course, you can make this function if you want to get the 5th element. That's not a big deal, but this is not a library function. So this guy doesn't exist. And this 3 car, CADR, etc., they exist in the scheme or Racket library. So when we have a possibility to construct functions, we can construct also objects of any type, any complexity. So here the first element is the list. And how many elements we have here? 5. 1, 2, 3, 4, 5. Length of this is 5. We construct the first element, the second element is 4, and this is third, fourth, fifth. So you have list of list and other elements. You can also have list that has here quoted list, and you ask what is car of that? 1, 2, 3. What is second element? Second element, of course, is CADDR. Third element, you have that this is 5. This one here returns 5. And then with evaluate, you can cancel the quote. So if I say evaluate quoted multiplication 2, 3, this is going to give me 6 because eval and quote are canceling each other. What you have multiplication of 2, 3. If you have 2 quotes, then eval will cancel 1 quote, but the rest will remain. So you're going to get that this is not 6, but it is 2 times 3, and then go home and compute that if you want. Or put eval eval. So these two evals are canceling two quotes, and then you get 2 times 3, that is 6. And you can cancel 3 of them or whatever else you want. Now, here comes something that is interesting, and this is a function that displays components of a list. So what I want to do, I want to have a write list function, WL, write list, that is taking the list and then displaying these components, 1, 2, 3, 4, up to the end. So 1, 2, 3, 4. How to do that? Well, usual tail recursion, you have a condition, and if the list is empty, return an empty object, so do nothing. If the list is not empty, then display the head of list, put one space, and write the function that is going to display the coder of list. The rest of list is going to be explained here. So this is the way how to write the list, first element, and then apply everything to tail of the list. So this is the way how we display the list. So here is display list 1, 2, 3, 4, you get 1, 2, 3, 4, or display list ABC, you get ABC. You see that Texas Instruments is case insensitive, so taking ABC, converting to uppercase. Racket will not do that. And so we have a variety of other examples here, none of them interesting, except this one here. This is something new, and we have to pay attention to that. Here is for the first time, lambda of x, and x is not in parentheses. What does that mean? That this is a syntax that is making something completely new. So what I'm saying here, I am writing this function w that has lambda of x, and then inside displays x. So what is x? X is the list of arguments that comes after the name of the function. So I have here function w, and then arguments are 1, 2, 3. So if x is not inside parentheses, then 1, 2, 3 are going to be packed in the list, and you will get this list here. And then this list is going to be displayed. So if I say w 1, 2, 3, then you have that this 1, 2, 3 is packed in the list. So now x is list. And then this list is given to this function here. And this function is doing side effects. It is displaying that on the screen. So I'm going to display this list. So if I define that as a function, for example, define w as lambda of x, and then write list, this is my function that processes list, you will get the same situation, w1, 2, 3. However, it is easier to write in this way than to write here auxiliary function. So all this works very nice. You can have write these three strings ABC, you get ABC, here they are. This here is not particularly interesting. That's the same thing that we already did. And now one strange program in Texas Instruments scheme that has gazillion of recognizers. There is no recognizer for list, which is unbelievably strange, but it is that way. So you don't have list as recognizer in Texas Instruments scheme. In the case of Racket, yes, you can have, for example, list as recognizer and ask whether where's question mark, whether 11 is a list. Of course, it is not the list, but this works. If you ask whether 1, 2, 3 is a list, of course, it is going to tell you this is the list. So Racket has list recognizer, and Texas Instruments scheme doesn't have it. So you can have frequently these assignments make your own recognizer. So this is a story how to write that program. And I made a couple of mistakes and I left them since this was stored in a script file. It was easy to put it in the reader just for entertainment of people. So what kind of function I want to write? I want to write a recognizer of list. So I'm defining function list with question mark and has list as the argument. So what I'm going to do, the first thing, condition. If this is an empty list, so if this is an empty list, then it is the list and return true. So this is the first thing. If it is not a pair, then it is not a list at all. So if it is not the list, it is not an empty list, and it is not the pair at all because it is number 6. So it is not a pair. If it is not a pair, immediately return false. So you see here, not applied to pair is list. Pair is asking, is this a binary tree that has left and right something? So if it is not tree, it is not a list, return false. In all other cases, check whether the tail is the list. So first, is the list empty? If it is, then this is the end of the story. It is the true answer. If it is not pair, return false. In all other cases, check whether CUDA is the list. Now we have to deal with vectors. Vectors are very similar to lists because lists have vector that can be written as list, but it has pound sign and not the quote. So vectors can be, as all vectors, indexed from 0, 1, 2, 3, etc. So we can go to Racket again, and we can define this vector V. And then if you ask what is V, it is giving you the vector. So vector has 1, 2, 3, 4, 5. There is also a possibility to define V and say create the vector. So there is a constructor, make vector. Make vector, and then you can say how many components you want to have in that vector. I'm going to have 7 components. Okay. So if I go here and ask what is vector that I created, it is vector filled with 7 zeros. So pay attention that these 7 zeros here that are a vector that we created are not going to be written in the reader as zeros because Texas Instrument has nice capability to put here empty objects that you can incrementally populate. So here you are making vector of 7 components, and you can also make this vector of 7 components, and you can put here the initial value of that. So when you do that, you have 7 components, 1, 2, 3. So the way how Racket is dealing with that, it's making vector that has 7 components. And if you put here nothing, then default values are going to be 0. If you put here 123, you get 123 or whatever it will put inside. Any object can be stored inside, can be a function if you want. So create a vector, make vector of 7 objects, and here is the object that is stored inside. So hopefully this is going to make clear difference between Texas Instruments that says define vector, make vector of 3 components, and you ask what is vector? These are 3 empty components. But this is very nice because it gives you possibility to build this step by step. So you can say vector set V of 0. So vector set is V of 0 equals 1, 1, 1, 1. So I'm making a matrix. This is the first row. And then I have a matrix that has first row and second row and third row unassigned at this moment. Then I can have vector set the third row, V of 2, to be 3, 3, 3. So I have first row, and this is unassigned, and third row is 3, 3, 3. And then I can do heterogeneous matrix. So vector set V of 1, second row, put here second row, you get first row, second row, third row. Or you can redefine this. You say V of 1 is 5, 6, 7, 4, and I have my matrix 1, 1, 1, 1, 5, 6. So first row, second row, third row of the matrix. You can reference any component. So vector of 1 is this row 5, 6, 7, 8. Or you can say vector reference of vector reference, second one. So this is 0, 1, 2. So it must be 7. 7 is here. Okay. So you can ask what is vector length. It has 3 rows. How many columns? Vector length of V1. It is 4. And vector is here in the form of matrix. Okay. You can also convert vector to list. Vector to list converter or list to vector converter. So you can also define that in the form by saying here is number of rows 5, here is number of columns C, and then I'm going to define a matrix, which is make vector of R components and C columns. So R rows and C columns, and comes matrix that is having 1, 2, 3, 4, 5 rows and 3 columns. In each row you have 3 columns. Okay, so it is also possible to create something new now. This is otherwise same as arrays in any other language. So there is nothing that I can tell you more than this. You have vectors. Vector can contain vectors. You can access each component. You create them incrementally, but as opposed to putting empty components, the Racket will put zeros inside. That's the only difference. Otherwise, works as components in any language. Now, an important thing, functions accepting an arbitrary number of arguments. So you can write either lambda of x without parentheses, in which case this is arbitrary number of arguments that are coming after this f, or you can put f dot x. So if you write f 1, 2, 3, 4, these 1, 2, 3, 4 are going to be packed in a list. And this list will be then evaluated by this expression. So I can say define some list of x, and I'm saying that if a list is empty, give me 0. Otherwise, add car of list with some list of tail. So how to compute sum of list? Well, you are adding head of list and sum of all components in the tail. Now, if we want to have some of those components that are after the sum, we want to make the function that is adding type your comments, no comments. So we have here sum of 1, 2, 3. We want to get 6. So how to write this function? You say I define sum of x, and here is dot or lambda expression like this, and then call this function sum list to x. So I can now say define sum x, and then put of x and sum x like this. So I can define this function, and sum x of 1, 2, 3 is going to be 6. Sum x of 1, 2 will be 3. Sum x of 1 will be 1. Sum without any argument gives me 0. However, look what happens here. This is the function of an arbitrary number of arguments. I can have 1, 2, 3, 4, any number of arguments, including no arguments at all. Sum works with that as well. However, if I have sum that has fixed number of arguments, so sum of two arguments, x, y, which is x plus y, then I can say, okay, sum 3 plus 4, and you will get 7. That's fine. But if I say sum 2 or 3, 4, 5, then this is going to create error message. Function expected 2 arguments, but was called with 3 arguments. So you cannot call it with 3 if it has 2. Now, it is possible to have sum of 4, 3, 2, 1, 0 elements, but you can make also the request to have a specific fixed number of arguments. And this is done in this way. So if I have this sum, which is lambda of x and some list of x, I can have sum of 0, 1, 2, etc. Elements. However, if I want to have required and optional arguments, then I can use things that need to restrict the number of arguments. Because if I have to compute mean value of these arguments 1, 2, 3, I have to compute some list divided by length of list. So if I have 3 arguments, the mean value is going to be 2. Mean of 1, 2 is 1.5. Mean 1 is 1, but mean of no argument is going to explode because it is dividing by length of 0. So it is division by 0 error. So you can define mean that has one mandatory requirement. So if you say you have to have one argument and other are optional, this is written as lambda, and in parentheses you put x dot y, z, etc. So the first argument here is mandatory, and these other arguments are optional. And then you say it is the same. Divide sum of x and some list of y. Divided by length of y plus 1. So if I say now, give me the mean of 1, 2, 3, it is 2. Give me the mean of 1, 2, you have 1.5. Give me the mean of 1, 2, 3, 4, 5, 3. Mean of 1 is 1, but mean of 0 argument is going to be invalid argument count. Function expected 1 argument, but was called with 0. So you have argument count error that is now we made. We can also ask, we want to have 2 required argument at least. So if you compute mean, you don't need to compute mean or standard deviation of a single number. So you say lambda of x, y, and z. X, y are mandatory, z is optional. And then you have sum of x, y, and some list of z divided by length of z plus 2. So these are these elements here. Now you can have mean of 1, 2, 3, 4, 5 works fine. With 2 arguments work fine, but mean of 1 is not going to work because it has no mandatory arguments. And this is all what we have for today. So what we did today was first control structures. Second, we discussed lists and list operations. And third, we discussed important topic of functions with arbitrary number of arguments, where some arguments can be mandatory, some can be optional. So these are plenty of things to learn when you see them for the first time. However, on Wednesday, we have no class. It is Veterans Day, which is observed. Therefore, we have now a whole week. And please try to go through these slides and experiment with them, the way how I played with them during this lesson. Then when you come next Monday, we are going to speak about first-class objects that are extremely important thing. And after that, we only have scope is simple, nothing, input output. So first class objects and file input output, and then we covered the whole scheme. We'll read a little bit reference card, but that's it, that's the end. So I can switch to studying Ruby. So now it's time to learn this and to try to experiment with that. Of course, a good way of experimenting is to repeating these things that are given here and looking how this works in Racket. You can use either Dr. Racket or Racket, whatever you prefer to use. And also, you can work on homework. Don't look at solutions of homework which are posted in the reader, but first solve in your way and then go to see how this works in Racket. Or do something that you have as examples. For example, solve quadratic equation. A quadratic equation is something that you solve in each and every language, so do it in Scheme also. Quadratic equation has these three components, x, y, and a, b, c, and then it has to return x1 and x2, and you have to write that. And you have some quadratic equation solver somewhere in the reader, and then check whether you have the same thing or something different. Is it working properly, etc. So if you have some questions, please go ahead. If not, there is office hours that are from 1 to 2.